Okay, so this is Unit 4, Presentation 3, and what we'll be talking about is stars and galaxies. So a little bit more than just our solar system. So the last couple weeks we've been talking about what's in our solar system. So now we're going to go beyond our solar system. So we're going to start talking about stars and galaxies. And one of the things that's really, really hard about discussing this stuff is talking about the sizes of things and the distances of these objects. Right? As of right now, if we wanted to go to any star or galaxy that's the closest ones, nobody could make it in the way we travel, in the speed that we travel. There's no way that in one human life. So if a baby was born on a spaceship, that baby wouldn't be able to make it to the next star in their lifetime. So that's how far these objects are away from us. So when you look up at the sky and you see all these stars, these are very, very, very far away. So these light is traveling an enormous distance to get to us. So these are the things that we're going to talk about. So first thing we're going to talk about is the stars. Again, remember when we take notes, we should make sure that we have our highlighters out and we have set up our notes. So the thing is, first thing, let's talk about what a star is. A star is just a hot ball of gas. All right. And that's it. It's got an iron core in the middle, and then it's just a hot ball of gas, and it's just hydrogen gas that's inside of it. And all stars come in 3 different sizes. All right, it comes in medium, huge, and giant. And we talked already that our sun, right, is a medium-sized star. Now I don't know why they didn't just call it small, medium, and large. This is the way they kind of came up with it. They said medium, huge, and giant is the biggest one. So I know huge and giant seem the same, but in space terms, when we're talking about stars, giant is the biggest. So this one is the biggest. And in a minute, when we get there, I'll talk about how big is a giant star compared to our star. All right, but our sun is one of the smaller ones. All right, it's not very, very big. It's a medium-sized star. Okay. So those are the 3 different sizes that stars come in. All right. Now, this is a big part is what happens to a star when it dies. It's just a star has a life cycle just like a human does. You know, they're born and then they eventually will die. All right. And the thing is the size of a star depends on what happens when it dies. Okay, so for a medium-sized star, so this is our star, right? What's going to happen is our star is going to turn into what's called a black dwarf. And a black dwarf just means that lights go out. That's it. So it's just like somebody turning off the light bulb. It's just this big iron core that's now going to sit in the middle of the middle of space, and it's just not going to create any more light. That's all it is. All right, a huge star turns into a neutron star. All right, so there's a picture of the neutron star right there. And then the last thing is a giant star. All right, giant, these are the big ones. These are the ones that turn into the black hole that people talk about. And what happens in a black hole? We're really not sure really what happens. All we know is that when a giant star explodes, so a giant star will explode. And when a giant star explodes, it's so big and it has so much gravity that it rips a hole in space. And that's what a black hole is. And if you kind of think of it, if you ever take a bath, right? And then you unplug the bath so that the water can go out and you see kind of like the water swirling, that's kind of what a black hole looks like when it's going through. And basically anything that's around it is going to get sucked into it. Now, what happens when you get sucked into it? It's anybody's guess. You know, some people believe that it takes you somewhere else. Some people believe that's where things just die. All right? So again, the size of a star depends on how it dies. Like I said again, our star will just eventually just vanquish, but that's not going to happen for millions of years. Right? I think like they've talked about how the sun is not going to die for another 4 million years. So for us, obviously we're never going to see our star turn into a black dwarf. Alright, so let's just kind of like, I want to just show you guys what I mean by the size of a star and the relationship between medium, huge, and a giant. So here are just 3 samples of what we know as a medium-sized star. So let's take a look at this. So the first one is a medium size. Our sun is 1.4 million kilometers. Huge star is almost 80 times bigger. All right, so it's star Rigel, 86,800,000 kilometers. And then a giant one is called VY Canis Majoris. I don't know how they name them. They just name them. All right, and if you see, it's 2,520,000,000 kilometers in diameter. So if I can just show you guys, just to scale it, just to show you guys what I mean by that. Let's say that I make our sun this big, right? And we did a scaling technique for the solar system. So let's say our sun is this big, right? What would, in comparison, a huge star, so star Rigel compared to that of our sun, would be this big. And again, I'm going to try and do the best I can to make a circle, but it's not going to be perfect. So that's how big a huge, so this is right here. This would be the medium. Right? This bigger one would be the huge one. Okay? And now what I want you to imagine is this. Look at the floor. Look at my room. All right? For the giant star. If you look at my room and now imagine a circle inside of this room. That's how big VY Canis Majoris is compared to our medium-sized star and a huge star. So look at the screen and look at the floor and imagine the entire floor being one big giant circle. That's how big a giant star is compared to that of a medium-sized and huge star. Very huge difference. Okay, so it can tell you how small our star is compared to some of the other stars that you see in the night sky. Oops. All right, so stars come in different sizes, all right, or I'm sorry, different colors, and the colors represents the temperature of a star. All right, so the hottest stars are going to be blue stars. Okay, so the blue stars are right here. That's the hottest stars. It goes in the same scale as your when you guys use like your stove. So if you have a gas stove and you turn the heat, you turn the stove on, you see different colors, right? You see yellow, you see orange flame, you see a red flame, you see a blue flame. Even if you're on a camping trip, if you make it stuff, you'll see all those different colors. Well, if you want to ever like boil something the quickest or whatever, you want the blue flame to be touching the actual part. That's the hottest part of a flame. You never want to touch that part. Okay, now the coolest part, I mean it's not really cool, but the coolest part of a flame is the red part. Okay, now our sun is about right here. It's orangish yellow. So it's not the coolest star, but it's not also anywhere near the hottest stars. And size really doesn't matter. Like some people believe that if it's bigger, it's going to be hotter. Not true. All right. You can have a medium-sized star that's also blue. All right. Now usually the hotter stars, the blue stars, they don't live as long because they're using up their gases a lot faster than say our sun. All right. Our sun uses up their gas very, very slowly, and that's the reason why the temperature of our star is very, very cool compared to something else. So the lifespan of a blue star is a lot shorter than, say, of a red star. Okay, so galaxies. Galaxies are a collection of hundreds of billions of stars. Okay, hundreds of billions. Our Milky Way galaxy, okay, so our Earth belongs to the Milky Way galaxy. All right, and that contains 200 billion stars in the night sky. Some people even believe that it might be even up to 400 billion stars. So it's hundreds of billions that we see. So all the stars that you see in the sky, those are all belong to the Milky Way. All right, we can't see outside the Milky Way galaxy, at least with our naked eyes. All right, and our galaxy is also considered a spiral galaxy. So if you look at the picture right here, this is what astronomers believe to be the shape of our galaxy. It looks like a spiral shape, and this thing just keeps spinning like this. Just like how our Earth rotates and revolves, so does a galaxy. Everything in space revolves and rotates around something else. Okay, so that's how galaxies are. And it's hard to imagine that this thing. And with galaxies contain millions of solar systems inside of there too, and stuff. Not every star has a solar system attached to it. Okay, our obviously sun was the right size, right temperature to allow for a solar system to exist. All right, but not every star. So not all the 200 billion stars that are in the Milky Way have a solar system inside of it. Some of them are just a star. So there's 3 types of shapes of galaxies. Okay, so 3 types. First one is a spiral. This is the one that we live in. Okay, it's shaped like a disc, like this, and it has like little arms on it attached, so it spins around. The next one is an elliptical shape, and that's this one. So elliptical is more like an egg shape. Okay, and then the last one is an irregular shape. An irregular could be any shape, really. It just basically means it doesn't fit. It's not quite elliptical, and it's not a spiral shape. So they call everything else an irregular shape. So like you might see some, galaxies that are weird shapes. Those are considered irregular shaped galaxies. Right? All right, and the last thing that we're going to talk about is measurements. Right? In our solar system, we used as astronomical units. Right? Now when we're talking about traveling from like star to star or galaxy to galaxy, we use light years. Right? And to give you just an idea of how fast a light year is or light travels. So basically, I'm sorry, let's just start this over again. Light years means how far does light travel in 1 year. Okay? And it's very, 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 very far. So imagine this. Light travels 186,000, that should be that, 1,000 miles per second. So every second, light will travel 186,000 miles. Okay? Now imagine how far light travels if you had an entire year. That's what a light year, that's what a distance is equal to. And like the closest, I think, star that we have to here is 4.3 light years away. All right, so now just imagine how far that star would be if it takes 4.3 years for light to travel to that next destination. Okay, it's very, very, very far. So that's how things are. I mean, if you're talking about like galaxies, I mean, the next galaxy is hundreds of millions of light years away. So like, there's no chance that, with our travels, we would ever get to another galaxy unless we came up with something totally different. So that's the reason why we use light years. So AUs only work in our solar systems. We use light years to explain distances that are really, 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 really far away from the Earth. Okay. And I have some videos. I know that I'm not showing you any videos, but I've got 3 or 4 videos that I'm going to show you guys that go along with these notes a little bit later. Maybe tomorrow. I'm not quite sure if we'll have time today to kind of show you all these different things that I'm talking about. All right, and that's it. And that's our notes for today. And so do your summary on another page.